Welcome. Today, we're diving into the world of approximation algorithms. These are your go-to tools when faced with problems that are just too hard to solve perfectly in a reasonable amount of time. Instead of insisting on the absolute best solution, we settle for one that's good enough, but can be found much more efficiently. So, when optimal solutions are computationally intractable, that is, they take too long to compute, approximation algorithms come to the rescue to find good enough solutions efficiently. So, what exactly are these NP-hard problems that force us to consider approximation algorithms? These are problems for which no known algorithm can find the optimal solution in polynomial time. Polynomial time means the time it takes to solve the problem doesn't increase too drastically as the problem size grows. Instead, NP-hard problems often have time complexities like order of 2 to the power of n, written as O2 to the power of n, or order of n factorial, written as On. As the input size, represented by n, increases, the time to solve these problems grows astronomically, making it impractical to find the absolute best solution for large inputs. Let's look at some classic examples of NP-hard problems. First, we have the knapsack problem. Imagine you have a knapsack with a limited weight capacity, and you're given a collection of items, each with its own weight and value. The goal is to select the items that maximize the total value you can carry, without exceeding the weight limit of the knapsack. Then there is the traveling salesman problem. Imagine a salesman has to visit a number of cities. The aim is to find the shortest possible route that visits each city exactly once and returns to the starting city. Approximation is the strategy of trading optimality for efficiency. In other words, instead of finding the perfect solution, we aim to find a solution that's within a known factor of the optimal solution, and we do it efficiently. So the value obtained from the algorithm is less than or equal to alpha times the optimal solution. The approximation ratio, denoted by the Greek letter alpha, gives us a bound on how much worse the approximate solution can be, compared to the optimal solution. For maximization problems, alpha is equal to the optimal value divided by the value obtained by our approximation algorithm. The algorithm gives at least 1 by alpha of the optimal solution. For minimization problems, alpha is equal to the value obtained by our approximation algorithm divided by the optimal value. The algorithm gives at most alpha times the optimal solution. Let's consider an example where a greedy algorithm is used. Take the set cover problem. Given a universe of elements and a collection of sets, where each set contains some of these elements, the problem is to find the smallest number of sets whose union covers all the elements in the universe. A greedy algorithm for this problem works as follows. While there are still uncovered elements, pick the set that covers the most uncovered elements. This greedy algorithm has an approximation ratio of the natural log of n, written as ln n. Another technique is linear programming relaxation. First, convert integer constraints to continuous variables. This means that instead of requiring variables to be integers, we allow them to take on fractional values. Then, solve the linear program optimally. This can be done efficiently using various linear programming solvers. Finally, round the continuous solution to a feasible integer solution. This may involve some clever rounding techniques to ensure that the final solution satisfies the original integer constraints. So the first step is to relax integer constraints. The second step is to solve the linear program optimally, and the third step is to round to integers. Now let's talk about PTAS and FPTAS. PTAS stands for Polynomial Time Approximation Scheme. The time complexity is order of n to the power of f of 1 by epsilon, written as O(n)(f1/epsilon). FPTAS stands for Fully Polynomial Time Approximation Scheme. Here the time complexity is polynomial in both n and 1 over epsilon, written as O poly n1/epsilon. Let's see an example of FPTAS with the knapsack problem. One common approach is to scale values. This involves reducing the precision of the item values by a scaling factor k, which is equal to epsilon times the maximum value, divided by n. The scaled value is equal to value divided by k. Then, run a standard dynamic programming algorithm using these scaled values. With this approach, you can find a solution within 1 plus epsilon of the optimal solution, and the algorithm runs in polynomial time with both n and 1 by epsilon. Here the time complexity is order of n cubed by epsilon, written as O n superscript 3/epsilon. To summarize, approximation algorithms provide efficient solutions to NP-hard problems. These algorithms involve a trade-off between solution quality and computational time. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.